So it's my great honor to invite my previous mentor, actually also my current mentor, Professor Metin SITTI, to come to our today's IAS talk. So Professor SITTI is actually the president and the professor of the College University in Istanbul right now. Formerly, he was the director of Physical Intelligence Department at the Max Planck Institute for Intelligence System in Germany. So I spent almost 14 years with Metin there, and he was also a professor at ETH Zurich, Switzerland. Before that, he was a professor at the CMU. And Professor SITTI actually got lots of prizes, including the ERC Advanced Grant and also the NSF Career Award and many others. And he is an expert in micro robotics and also relevant areas. And I actually wrote many things here. For example, like he mentored like over 70 PhD students and 80 postdocs, where over 65 of his group alumni are professors right now around the world. I actually wrote even more here. I don't want to read it anymore. The most important thing I want to see here to other people also to Metin is, I believe Metin is not just a good mentor, he's also a good friend of me. In addition to that, he actually taught me how to do research, but in addition to that, he also taught me how to be a good researcher and a good person. So without further ado, let's welcome our talk. Welcome Metin today to give us a good talk.
Thanks for the great invitation, and great to see you here first time in this campus. But a pleasure to talk about our small-scale robotics work for medical applications inside the body. So as Metin mentioned, today I'll talk about the work we did in Max Planck Society. As you might know, Max Planck Society funds basic research and applied research. And I was there around 10 years. Metin was one of my best postdocs. And I trained a lot of postdocs and PhD students. The numbers are always increasing. And I have now a new group at Koç University focused on medical applications of our miniature robots I'll show today. Many of them are faculty now. Around 20 of them are in China and Korea later, and Turkey and US. A lot of them are in US also, and also many in industry, and we have also several startups. Before I talk about my science, let's very briefly let me tell you about Koç University, where I'm now the president and also doing active research. If you have ever been in Istanbul, it's a huge city with over 20 million people. This is Europe, this is Asia. So this is the only city in the world. A sea passes from the middle, and you see Asia from Europe. So our university is in this corner in this beautiful forest. It was built around 32 years ago, and airport is there. And we have also a great hospital and medical school around 30 minutes away. So this main campus includes all the other non-medical fields, and it's a beautiful campus, and we look forward to having you there. So we are private, everything is in English, like here. We are top #1 research university now in every field of research. In Turkey, there are 52 ERC grants, which are given to individual faculty in the EU, and out of 52, 32 of them are in our university. So just showing how the quality of the faculty and also students are amazing. But I hope we will have partnerships with your university in the near future and exchange programs very soon. So let's go to science. So let's start with some medical problems inside our body where we might have very difficult ways to treat. If you have, for example, in your brain vessels an aneurysm, which means thinning down of the wall and creating this basically blood pressures inducing this balloon and eventually collapsing and bleeding, and you will die if you don't treat it. And the same, if you have a blood clot happening by time due to different reasons, you will have a stroke, and that can be, again, damaging your brain, or you can also die. And these are, of course, problems happening in very small regions of the brain vessels. And if you're lucky, the doctor takes CT and MR images of your brain when you have these problems. You need to be treated in 1 day. And if you're lucky, around 60% of the cases, the problem happens in bigger vessels. And then what doctors do is they can open a hole from your leg and push a catheter to your brain through the heart. And then this catheter can have a tip which can basically have a suction tool that's called thrombectomy, and so that they can basically take the blood clot, or they can deliver a stent into the aneurysm area, and then they can treat the problem. But however, many of these diseases, like 20-30%, happens in smaller vessels, and catheters cannot access. And those cases, they need to do major surgery, and then you will not survive it, or you will have a lot of damages left behind. So in that sense, we are looking for new technologies to reach to even smaller regions that catheters type of tethered devices cannot access, or very risky to access. And that means we need to become now wireless, so that we don't have any tether, and we can also like to be smaller than a catheter, which is typically millimeter scale. So not only brain vessels, so this is the real picture of brain vessels, guys. I mean, look how complicated and how small it gets. Again, if you are lucky to have the problem in the bigger ones, the catheter can access. But if it gets in the smaller areas, we need new devices like wireless devices. And also the nice thing about being wireless is after we enter to the body, any region like brain vessels, or also the problems happen in many other parts in the body which are hard to access. And we can leave the device inside because they are wireless. And then if the problem happens, we can treat it again. So the wireless devices have also that implantability kind of advantage. However, if you are wireless, of course, there are a lot of scientific challenges, because catheter, you can give power from the catheter, you can have an optical sensor, and that makes life very easy. But if you are with no tether, you need to miniaturize everything, including power, actuators, electronics. That's very hard. That's why you need to find new techniques. And if you're a very tiny wireless device, how to fabricate them, how to track and control them, and also how to navigate them in the body in these complex parts with different methods are big challenges. And the biggest challenge will be, of course, how do you make sure that any wireless device inside your body will be safe? So in that sense, we have been doing a lot of research in my group and around the world in many different groups. But the first wireless miniature device concept was indeed in a science fiction movie. Before we were born, all I think in this room, including myself, 1966 was the Fantastic Voyage movie that you might have seen or heard, and the newer version is Inner Space by Spielberg in '87. So the idea is how to miniaturize a machine and inject to the blood, and they would navigate in the blood vessels and reach to the brain, and then they treat a famous politician. They open the blood clot by a laser so that they could treat the patient and the person. So these were, of course, great science fiction, but look, it's been 60 years now, is it right? Now, let's see in 60 years what we have achieved as engineers and scientists after having this first movie, imagination. So if you want to build any tiny medical robot or device that will go in the body, there are a lot of puzzle pieces we need to solve at the same time, holistically. We need to design and manufacture them with new materials. We need to deploy them and retrieve them from the body. Some cases we will inject to the blood, some cases we will swallow, some cases we will deliver with even other techniques. And then we need to take them, or they need to dissolve in the body. They need to have functions like they can deliver drugs, they can do heating, they can do embolization. Many functions they need to achieve to do treatment, or they need to have some sensors to do diagnosis. They need to interact with the human body cells like immune cells, blood flows. Many biological interactions will happen, and we need to make sure that they are all friendly and they don't cause any negative effect. We need to be able to track them with medical imaging, so we need to see where they go, what they do to be safe, and eventually also use that for actuation and control. So we need to solve all of them, unfortunately, at the same time. And these are topics that you need really a great team of people with engineers, scientists, even medical doctors all together. So I have been teaching microrobotics since my Berkeley time when I was a postdoc. And although I haven't been teaching after United States, I finally wrote a textbook on this field after teaching so many years. And the good news is just recently, although you guys don't need because your education is in English, now it's translated into Chinese. So this is the book talking about different methods of how to design, fabricate, and control tiny machines in the body or in general. Also, there are other applications, of course, of these tiny machines. So the first approach of making a wireless cell-sized or even bigger robots is what we call self-propulsion techniques. Self-propulsion means a synthetic robot, for example, in this case, this tube has plutonium inside in the inner wall of the cylinder, which interacts with the chemical in the liquid medium, which is hydrogen peroxide. That interaction induces catalysis. Catalysis induces bubble, and that bubble induces propulsion. Because of the anisotropic shape and the bubble is released from one side, you have a propelled robot, self-propelled, because it has nothing else to do, just interaction induces, in this case, chemical interaction induces propulsion. The second approach is you can use live cells like bacteria, algae, any microorganism that is small enough and active. You can integrate the robotic bodies, and that's what we call biohybrids. Even these days, people use cardiomyocytes, so you can have cardiac cells also for active propulsion. And then we can harvest the motility and sensing and other capabilities of the cells, while we can remotely control them or other way control them as a robot, so we can program them as a robot. So I will tell you some examples now in both approaches. Of course, we have been doing a lot of examples, but let me give you an example of synthetic self-propelled micro-robots. In this case, rather than the chemical interaction with the medium, we use light interaction. So I have been collaborating with a neighbor institute in Max Planck. So they could synthesize these very small particles with nanotexture, nanoporosity, in the solar cell applications, for energy applications, because when you shine light on these particles, they induce charge because of photocatalysis. And the charge distribution around the particle with nanoporosity is typically asymmetric, and then that induces voltage difference that will create a propulsion of the particle. So we said, why don't we inject these particles, in this case, inside the human eye? Because if you're in the eye, we can use a light source to steer these active particles to a target retina region for delivering drugs for treating some eye diseases. So this approach was great because just shining the light, and depends on which direction you shine the light. For example, if you shine the light to the left, the particles actively follow light. In this case, it was shined to the center. Let me show again. So basically, we call it phototaxis. These particles could be steered by the light source direction. So if you, again, you see in the video, the second one, it's centered. Basically, they follow the light gradient. More quantitative data here. Of course, you need to do hundreds of thousands of measurements. People have been doing these kind of things before also. We were not the first. But they always worked in water where there is no ionic medium. But when you're in ionic medium, typically these particles, typical ones, were very small propulsion. But for the first time, with this nanoporous new carbon nitride material, we could show that in ionic media, you can get also relatively good mean speeds. Don't forget, these things are only 1 micron size. So if you have 20 micron per second speed, that means in 1 second, you move 20 times your body size. So they are really fast. Of course, parameters important here are one, wavelength of the light. Typical wavelength is around this close to visible light, and around 415 also they work, but the charge generation is not efficient. Then you don't get too much propulsion. But the ionic media again could work with no problem. As I said, the light following, it works greatly because of when you shine the light, one side is more illuminated than the other side. That's why charge is more in the one side. That works to our advantage. Then the propulsion is directional to the light source. So, of course, anything you make and put inside the eye or body, they will interact with the human cells. And we need to make sure that they are not toxic to the human cells. Then you need to do a lot of experiments. So these are biological cells that we have in our body, so fibroblasts and these human cells. And what you do is you put all these particles in different densities onto the surface of the cells. If the cells still keep growing with no change, they are called viable. That means they are happy. That means there is no toxic effect, and the particles are biocompatible. But if you see cells dying too much, that's not good news. That means particles are toxic, so you cannot use them for medical use. So we optimize then the density of the particles, and as you see in some cases, there will be some issues. So we optimize the density according to these data. So after you show that they are biocompatible, next is you need to show they are functional, because we can actively steer them to the retina, but then when they reach there, they need to deliver drugs. So thanks to the nanoporosity on the particle, we can load them with small molecules of drugs. As you know, drugs are small molecules typically. In this case, doxorubicin is a famous classical tumor cancer therapy drug, chemotherapy drug. And we can load them to the pores. And when you shine the light, they also depends on the oxygen level of the environment. If there's less oxygen, they release more. And that's a good thing, because when you have tumor in the eye or anywhere in the body, typically it consumes too much oxygen. That's why it's better for us that they deliver more drug to the tumor region. And also pH in the environment is important. And also when there's tumor, is pH low or high? Do you guys know? Or neutral? When you have tumor, pH is low. They are acidic media. So in that sense, they are also triggering more drugs. So this is a typical way most of the drugs work. When they reach the tumor area because of lower pH, they will basically create more release of the drug. So that's the function. And of course, now you need to show them not only in data, but in reality. So we took a real pig eye with the fluid inside, very fresh from the slaughterhouse. We inject the particles. You see that by the illumination direction, we can basically control their flow to the retina. And here, this is images from OCT, and the resolution is very high. You can see almost individual particles. But the interesting thing we observed when we do the real biological experiment is inside the center of the eye, there is a vitreous fluid, which is very fibrous. The particles couldn't move in the vitreous part, which is very viscous and very heterogeneous, but they could move around the perimeter, which is more aqueous. So that's why the medium, the complexity affects a lot how these active microparticles or robots are moving. So in that sense, these are ongoing research right now, and we will try in real animal, live animal. This is a dead animal. And then we can treat some of the retinal diseases very locally in a very precise way from now on. So as the second example, let's move to the biohybrid example where we can use live cells. In my group, we have been working almost now 15 years or more, how to use live bacteria. Because bacteria, as you know, are typically pathogenic, and we always have a negative image. But indeed, these days, everyone knows now bacteria are indeed very friendly for our body. So microbiome in our intestines are helping for our digestion all the time. How much bacteria an adult would have in the body? Right now in my body, how much gram of bacteria I have? What do you guys think? Is it 100 gram, 500 gram? Do you have any guess which help my digestion, even my brain psychology? So if you have a problem with your bacteria, you will have a lot of diseases. How much? Half kilo? 100 gram? Gram? More? It's, huh?
1 kilogram.
1 kilogram better. So it's 1.5 to 2 kilogram. So almost 2 liters of bottle of bacteria is now in my body, in microbiome, helping digestive system. So in that sense, there are many friendly bacteria. So we take E. coli, which is typically not friendly, but we genetically engineer it to make it non-pathogenic. And even we can engineer it genetically so that the surface of the cell membrane of the bacteria induces biotin molecule that we can genetically engineer in collaboration with some scientists. And then we can make cargo of a robotic body where we fill, for example, in this case, red blood cell with a cancer drug and also magnetic nanoparticles inside. These are doable things. And this is the real image how bacteria sticks with the cell membrane to this red blood cell. As you know, red blood cell is a passive cell, but if you attach it to a bacterium with our technique of the chemical binding, we will see that indeed red blood cell can be propelled with the bacteria that is pulling it. And because of the magnetic particles on the red blood cell that we attach to bacteria, we can steer precisely with remote magnetic field control. So here the field direction is changing with a magnet from outside. We can steer it in the body to the right direction. These are interesting systems because when you put them in the blood vessels, they will go even your brain microcapillaries 2 micron, and red blood cell is 7-8 micron. If you look at it, red blood cell is so elastic and bacteria is so small. They can pass through, so the bacteria can pull it through the microcapillary so that we can move in the brain vessels and everywhere with no problem. So again, we need to do a function with it, and in this case, besides magnetic particles and chemical drug, we add inside ICG molecule of the red blood cell, again, cargo we carry. And then the nice thing about ICG is when you apply NIR laser, as you know, near-infrared laser can penetrate skin until some depth. So how deep an NIR laser can penetrate our skin? Anyone knows? Of course, depends on the intensity. Is that right? So typically, a centimeter is doable. Up to centimeter deep in our tissue, we can have light passes through the tissue without damaging it. And then ICG molecules absorb the NIR light, heat up. As you see, it can heat up to even 60 degrees. And that heating up has many functions. So when you have remote heating that we control on demand in the local area where we reach, we can create hyperthermia. If you heat, as you know, when you have fever around 41 degrees, if you don't get it done, you will die because it will degrade your enzymes. That's why if you have 44, 45 degrees of a temperature by a medical device locally to a cell, neighbor cell, you will kill the cell, okay? So that's why hyperthermia is a method that if you locally go and heat the red blood cell with the NIR light, it will kill the tumor cells, neighbor tumor cells. And at the same time, the red blood cell will, because of temperature, will explode. And when it explodes, the drugs will be fully delivered locally, which is a cancer drug. It will also kill the tumor cells. And then the nice thing is, when you heat up, also not only red blood cell explodes, also bacteria die. They also cannot survive much temperature. That's why when we do bacteria removal, we just heat them up, is that right, by hot water. And that way, we can also kill the bacteria and nothing is left behind the operation. So in that sense, this was the first time we showed that bacteria-driven cargoes can be reaching a target and delivering drugs, and also hyperthermia with all these functions at the same system. So these are things we are now trying in the live animals, but I will skip the details to go to the second approach. So rather than self-propelling robots and cell-size robots, we can also talk about externally driven robots. So rather than self-propulsion, we could use magnetic fields or gradients. Like these are great examples since almost 25 years. In Japan and ETH, people have been using magnetic elements and spinning them or pulling them to create actuated very tiny devices. You can use electrical fields, but that doesn't work mostly for a medical application. Light is possible, but tissue penetration, as I mentioned, is limited. And the second very popular approach is acoustic waves. If you use acoustic waves, you can also create propulsion and control on tiny machines. So I'll show you both examples now. Let's use acoustic ones first. As you know, sound waves are easy to generate. Use a microphone, which is a piezo ceramic. And control the frequency that you create the oscillation of the piezo. And typically, we go very high frequencies above our hearing, above 100 kilohertz. So here, we design these days and fabricate very tiny robots at the cell size using 3D printing. As you know, 3D printing is everywhere. Using 2-photon polymerization, you can have commercial printers these days with 100 nanometer resolution. And here we design an internal cavity of sphere where we have a nozzle. This is the nozzle cross-section, encapsulated inside this bullet-shaped robot. So what happens is if you put this internal cavity robot with 3D printed polymer inside water or liquid, it will trap air inside, all right? And then we will show you now, if you have air, what will happen. So if you have air in this spherical cavity, well, what happens is it has this water interface in this nozzle area, which we control the exact shape. And at a given resonant frequency, the bubble will oscillate the maximum, and that will create a lot of fluid flow around the nozzle. Because when you oscillate it, it creates flow locally. You see the flows around it is very fast, and the frequencies are around 327 at the resonance. So what happens if you resonate and create the fluid flow? Look, you can propel crazy. This is slowed down video. But if you look at it, it's randomly rotating, all right? To make it go straight, I said to the student, okay, why don't we put a small fin geometry, which induces asymmetry. And when we do that, you see the small fin there. It creates the flow, not going randomly around the robot, but making a directional motion. But of course, the direction here is also random. Okay, but the propulsion is amazingly fast. That's the great thing about acoustic waves. And our body, with ultrasound imaging, if you have ever tried, you can go deep into the human body with no problem with acoustic waves. We are transparent acoustic waves, with some, of course, attenuation. But if you put a magnetic film onto the same robot, now we can precisely control exact direction it moves rather than random. You see that we can control with a computer to go exactly which direction, but the speed is really amazing. So in that sense, it's a very hard control problem. But this is, we don't need very precise control in medical systems, so that's not a big problem. Okay, so I showed you the nice motion videos, but they were in water. Water is easy because viscosity is low and it's Newtonian fluid. But if I go inside the human body, I have blood, I have mucus in the GI tract, I have other fluids. And water kind of materials depends on the shear rate, always constant viscosity. And we can change the viscosity by this kind of different mixing with glycerin to get more viscosity. But if you take any body fluid, you see that except urine is Newtonian also. That's the easy one. But for example, look at blood, which is the most important fluid in our body. With the higher shear rate, it gets lower viscosity. So it's not constant viscosity. So that's called shear thinning, so that when you shear faster the blood, that's why we have a pulse-style flow in the blood vessels. That makes it very easy to flow when you have high shear. That's why our heart needs to create very high pressure fluid flow to create easy blood flow. But again, these are complex fluids. We call them non-Newtonian complex fluids. And nobody showed propulsion in these complex fluids, especially mucus. As you know, mucus is in our GI tract, and it protects us from bacteria and many foreign other objects, it's very hard to move inside. So, but with the acoustic propulsion with high force that I showed you, now we can try what happens in these complex fluids. So when there are different viscosity, you see that the speed gets lower when you have higher viscosity. And now if you go inside the blood or the mucus, which is the hardest fluid, nobody showed a micro robot moving in the mucus other than a chemical trick, I'll tell you. And physically, this is the first time we show that with the high force of this bubble oscillation, we could move in the blood and also inside the mucus. In the mucus, one bacterium can swim. As you might have heard, what's the name of the bacteria that creates in the stomach cancer, and they live in the stomach? And you should definitely have a checkup to make sure that you don't have that bacteria in your stomach. What's the name of it? Anyone knows? Have you heard H. pylori? If you haven't, please take a note. You should go to your doctor and say, I need a test for H. pylori. So it's proven, and it's a Nobel Prize winning discovery, that this bacteria can go in the mucus. They release a chemical that makes the mucus low viscosity using chemical tricks, so that they can swim in your stomach mucus. They can penetrate your tissue and create ulcer, which turns into cancer later. So in that sense, that bacteria is now everywhere in the food. So that's why make sure that you get checked up, and you need to use antibiotics to get rid of it. So now the robot I showed you moving in mucus and other cases was always moving on the surface, sliding through the surface. It needed surface. But then we said, okay, in medical applications, also in the urine or in other areas like eye, I also need to move in 3D to propel. So then we developed and 3D printed more complex robots, which looks like a sphere now rather than a bullet. And we use the bubble oscillation idea. But now we make these nozzles now many facets on the surface, and each of them has different size and geometry. That means at different resonant frequency, one will oscillate and not the other. So that means like any robot, if you have ever seen a robot moving in the microgravity space, what you do is, since there is no air, it's vacuum, only way to propel is you make jets. That creates momentum transfer, and the nozzles, depends on which nozzle creates propulsion, your robot moves in the space. And the same idea here in the fluid, buoyant fluid, the robot will propel with nozzle that we activate will create propulsion. Of course, when the nozzle is activated, it doesn't only do linear propulsion, it also do rotational propulsion. So we can now excite different nozzles. This mode is creating helical propulsion. This is just published this year. And if you activate another nozzle, it will turn around, that's spinning. As you see, all the different dynamics is only controlled by changing the frequency of the acoustic wave. So as you see, the frequency and amplitude is changing. In this case, they move linearly, and everything is happening, by the way, in 3D in the liquid. It's not on the surface anymore. So that's a great advantage. So all these modes are, again, precisely controlled by frequency. And now we can make 3D robots that are moving in different fluids in the body. Another recent study is, rather than precisely control acoustic robots, we said, OK, in the blood, especially stroke application, we basically now want to trap a lot of these particles into a bigger group, like a self-assembly. To do that, we use now a focus ultrasound. So you can focus ultrasound waves using some transducer idea. And this focus ultrasound now, what it does is we created these new particles that have been used in material science for different purposes. They have very interesting flower-looking nanostructures with self-assembly. You can manufacture these things in kilogram very cheaply. And they're around 1 micron size. Because of this nanotexture, again, nanotexture is very important. Very interesting thing we observed is they create very high contrast under acoustic wave. The radiation forces are very high so that they can attract each other. And even when the blood is flowing, we can trap them. So it's kind of a trapping idea now, so that when we trap these particles to a bigger blob, we have much higher force. And if you have a blood clot here, we can go and open it. Using chemical tricks and also mechanical tricks. And the good thing about these particles are, again, they are very cheap and easy to make, and they are very stable, because when you apply acoustic waves under these particles, if you use a micro bubble, for example, they will collapse and they will be not stable. But these are solid particles, they're highly stable. And we have a new study, we tried them in the real animal, and we can treat the stroke. It's under review in Science Journal right now. So hopefully we can show that these kind of trapped acoustic particle globs or assemblies can treat some diseases in the blood vessels, like I showed you before, like stroke. So, OK, now let's go to a second approach rather than acoustic waves. What about we can use magnetic fields and gradients? And we do many studies on that, but in the sense of cell-sized robots, what we developed before is we coat a microparticle, which is silica, with half magnetic material and other half with antibody that detects tumor cells and also drug molecules. Because what we said is, OK, we are again challenging the blood vessel type tumor applications. If you have a blood flow and if you're a microrobot, can we ever go and move on the surface and stick to the tumor cells? And after we stick, we apply heat or we apply drug so that we can kill the tumor cell and treat the patient. So we got inspiration from white blood cells. Because this is the real blood flow in your vessels, and these are small vessels. The bigger ones are much faster even. So very interesting trick that white blood cells do is if you look at carefully, they roll on the surface when they want to basically move against, or if they want to go and stop and penetrate the tissue of the blood vessel. So we got this inspiration on surface rolling, and now this particle is rotating and rolling on the surface of the tissue. The only trick is the rotation of these particles needs to be 50 hertz. 50 hertz means in 1 second they are spinning 50 times. Okay? So that's why is that important? Because, for example, if I'm moving in the blood vessel with the flow of the blood, first, of course, again, the Hall coating will help me that if I'm moving on the cancer cells on the blood vessel, I can stick to them. If they are on the healthy cell, they will never stick because antibody will not recognize it. However, if I'm in the blood vessel now and I'm moving the particles, but I'm going to a channel to reach to a tumor, but suddenly I figure out, no, that's the wrong one. Doctor says, I need to go there, not here. This is the first time we showed that in this science robotic study. We can roll with a high frequency and go against the blood flow. Again, blood flow is crazy, and these are real blood, by the way, in the channel with this kind of flow of shear forces. Because of surface rolling at high frequency, we could move against the blood flow for the first time so that we can go to the correct vessel. That's great, but can I see them in the real animal? They are so small. They are only 5, 8 micron, 10 micron. Answer is yes. Of course, first thing is they are yes if you use photoacoustic imaging and MR imaging. Depends on how many of these rollers, particles you have. If you have 200,000 of them, you can see them with photoacoustic, you can see them with MR in large numbers. Okay? And the good thing is, of course, for tumor treatment, we need them in large numbers. However, in the brain vessels, when we are moving these small robots, I want to also detect them single. And the good thing is with the collaboration at ETH with Daniel Rezansky, we have shown that photoacoustic imaging where you send pulse light penetrating the tissue, again, this NIR light, so can go even up to 5 centimeters if it is imaging because the pulses are very low power. They can reach to the 5 centimeter deep and then send acoustic waves, and we can detect them. You see these green dots are indeed single particles. Of course, to get very high contrast, you need to coat them with gold and ICG to have NIR light absorption the best. So the good news is these cell-size robots can be seen. This is in 3D, so we are seeing blood vessels in your brain, in this case mouse brain, in real time and in 3D, so that's an amazing technique. The only problem is it works only a few centimeters deep in the tissue. If the tumor is very deep in the body, this technique wouldn't work. Then we cannot see single particles, then we see swarm of particles. Okay, so this was very small size robots, but indeed in our group we also went and designed milliscale robots, much bigger ones, and used soft body deformations for creating new medical robots because we looked, again, nature, as you see here, jumping and also in a channel moving. This is a C. elegans worm, this is a normal caterpillar worm. You can see that they can have very dynamic, physically adaptable, and programmable, shape programmable dynamics, which can create many interesting locomotion and functions, and they are soft and they are safe. So looking at these animals, we said, can we make them synthetically? And with a lot of studies, indeed, Wenchi was the first author. He did 4 years of work to get this breakthrough paper published. We could fail and we could be losing 4 years, but we didn't. So because persistence in science is very important if you have a great idea. So our idea was, we said, okay, let's take an elastomeric soft sheet or membrane, and inside magnetize the particles that we embed inside in a waveform, which is easy to create by basically rolling the sheet around a cylinder. At the beginning, particles are not magnetized, and when you apply very strong fields, they get magnetized, and if you open it, it's a waveform, okay? So this waveform is interesting, and this was a breakthrough study which was publicized around the world, and New York Times called it worm mates because it looks like a worm. To do all the actuation first, you need controlled homogeneous fields in 3D, which can be easily created with electromagnetic coils. Again, you need to design these things which are not hard, but it needs some electromagnetics knowledge. So if you don't apply any field, the sheet is straight and total magnetization is 0 because it's a one wave. But if you apply a small wave in this direction, it can create a sine wave. Another direction can create a cosine wave. Another direction with higher field strength, which is only 20 millitesla, U-shape or V-shape. And we can create controlled deformation modes. And when they deform, total magnetization is non-zero. That means we can also rotate the body. So with all these modes and the body rotation, now we can make exciting actuation. And make this robot first make in a U shape, rotate it as a roll like a wheel, like the worms do, and undulate and create a traveling wave. And then you can swim underwater, on the water. You can swim like a jellyfish, all only by changing the external magnetic field waveform. Of course, we studied a lot for each, in this case, water meniscus climbing and then walking like a worm. Each of them has different waveforms that we optimize by studying, and they can even jump like the worms. And all these gates are, again, controlled in the same robot. So this is the first time in the robotics, so this is the highest cited robotics paper, because a same robot achieving all different modes of locomotion by just changing the external field so that we can go in the even complex environments. So this also received the Frontiers of Science Award this year. Why this is important? Because if you put them inside your body, first we have cylindrical channel, which we use in this case a new mode of helical propulsion. And if you get in the small cavity, we go undulatory wave, traveling wave to propel by swimming or surface crawling. And when you get in the bigger cavities, we move by rolling locomotion. So in that sense, our body has all this complexity. So if we didn't have this shape programmable robot, we couldn't navigate through this complex environment. Also, we added sticky feet to the same robot later to also make it climb onto your stomach or GI tract surfaces. This was a 9th mode. And then we could also treat some diseases in the GI tract. As a medical function, another animal was inspirational for us. Have you ever seen pangolin? I don't know if it exists in China or Hong Kong, but they exist in Australia. So when they are in danger, their scales is designed in a way that they can become a ball with large deformation and they can escape. We took that idea and made these metallic sheets embedded onto this worm-made soft magnetic robot. And why we cared about metallic sheets is because remotely, when we reach with the locomotion modes to any region where you have a bleeding or tumor in the small intestines, which we cannot access with other technologies. And after we reach there, we go flat mode, and then applying external high-frequency magnetic field, the metal sheets heat up a lot because of eddy currents, and suddenly you can heat and stop bleeding, or you can kill the tumor cells, as I mentioned before. So these are functions now we can add to our worm mate. And another mode we enjoy trying is rather than one single soft robot worm mate, we made large number of them because we wanted to create these cilia like biological cases. As you know, in our body, respiratory system and brain ventricles have the cilia. What do they do in our body? They pump the fluids. And they also transport objects, like you get these things to your throat. So they are very important for brain fluids, motion, and many other biological functions. So the synthetic cilium we did with the soft magnetic actuation is, again, the waveform. But in this case, we control the phase difference of the wave. We can shift it. And by optimizing its angle, the left and right motion induces this asymmetry at this length scale with the low Reynolds number. Viscosity or viscous forces dominate. So if you moved left and right the same, there will be no fluid pumping. It will move the fluid right and left, effectively zero propulsion. But by moving this asymmetry with sweeping area maximization, we can create the maximum fluid pumping. So then, rather than one cilium, we need to make a lot of them as neighbors. And here, if you make them all synchronous, they will create pumping, but not effective. But we discovered, and this was known in theory, that if you induce phase difference between the neighbors, there is an optimal phase difference of timing of the motion where you get the maximum fluid pumping. That's called metachronal wave. Indeed, the biological cilia you saw also has the same wave. And this was the first time we experimentally showed that the metachronal waves happen in this specific phase difference and maximizes the fluid pumping. This is the fluid flow. So that was great because that means if you have a disease where your cilia biologically doesn't work, we can now implant into your body these synthetic cilia, and externally actuate them and move the fluids like in your brain or in your respiratory system. However, this is millimeter scale, bigger structures work well, but they are too big. So recent study where Wenchi is also co-author just accepted the nature. We could miniaturize them now into the real biological cilia's length scale. This is diameter 2 micron and height is tens of micron. So you see that now, rather than magnetic, we do local electrical actuation. It's a hydrogel material that's very soft. However, with the electrical field we apply, we can, in very high frequencies, this is look at the speed, we can individually control each cilium. That way we can control fluid flow in a very precise way like the myological cilia and at the same length scale. So why is that important? Because depending on the way you control precisely the waveform of the individual cilium, so these, this, for example, object we can transport now, as you see, by just individually controlling, we can control exact trajectory of the fluid flow and the object transport because of array of each cilium are actively controlled and can be changed immediately because of electrical control. So again, these are developments that are exciting for different applications. But another organism and an inspiration again is jellyfish robots. Baby jellyfishes are highly interesting. They swim very efficiently. This is the first time we could get also best paper award. We could mimic a biological organism at the same size, scale, and the same fluid dynamics and aerodynamic. So you see the fluid flow around the robotic one. This is the dye moving around the jellyfish robot is exactly the same with the biological one so that we can create very efficient swimmers with a lot of interesting functions. This is the biological baby jellyfish. This is the synthetic one. In this case, each of the worm mates are 8 legs. And we have some tricks of the also other feet you need to design and manufacture. And now we can use the functions of this jellyfish robot. We can trap drugs fluidically without mechanical holding and releasing the target. Or we can put some fin around them and the jellyfish robot can go and clog some abnormal vessels bleeding or fallopian tube of, if you don't want to have a baby, you can close your tube and then open it when you want to have it. So the same robot also we use in the bladder. When we wanted to anchor to the bladder with a needle, we use remote heating of this adhesive that released the spring-loaded mechanism. And this jellyfish robot basically anchored to the surface where this silk needle degraded by time and delivered the cancer drug under tissue because the bladder cancer unfortunately happens under tissue. And this was a great way to treat it. And this is how strong it can basically engage with the tissue you can see with the needle. So we can also manufacture more complex soft machines rather than sheets or jellyfishes. Now we can go ahead and make much complex soft magnetic machines by assembly. This was with another Chinese student. He was very skilled in assembly. This needs hours of assembly with a lot of steps. But it's possible using 3D printed jigs and jig-based assembly. So now we can make more complex machines. So this is a soft capsule, very small, like 0.5 millimeter. With all these elements assembled together with a nozzle, we can inject drug before. And by rolling on the tissue surface, when we apply high field, we can release the drug on demand in a local area so we can treat diseases with local active drug delivery. We can do the reverse. We can make these also complex capsules that can open the valve with a triggered high field. And then inside now there was air rather than drug. If there's air, the open valve and they open this tail will move the air out and get the fluid in. That means we can take fluid sample from the human body, which is very important for diagnosing, for example, pancreatic cancer. So we can go there into the duct and collect the fluids and get out and do some DNA analysis to show that you have cancer or not. For diagnosis, liquid biopsy is a very interesting new discovery technique. The final example I'd like to give is a stent-looking soft machine. In this case, it's a metastructure. This is a soft magnetic composite in the milliscale. And the idea is, again, we want to go back to the original problem I mentioned to you into the small blood vessels. Here, we use a magnet that is more controlled by a robotic arm and rotating and moving. And if you rotate and move the magnet, the robot spins and pulled. And in this case, there is a flow of the blood in the channels. You see that we can, because of the soft magnetic structures, it can adapt passively to changing blood vessel diameter, plus can be bending to any channel of the blood vessel we want to reach. Even we can turn very sharp corners and go to all these curvatures with no problem, because again, if you remember, the blood vessels in our brain is so complex and we need to sometimes turn really sharp corners. So the good news is now this device can do it. It received a breakthrough award at that time when it was published. So if you make it out of hemocompatible material, which doesn't induce blood clot because of the material, that's doable with some film coating. You see that the device actively controlled moved to this aneurysm region, and when you put it there without any other function, it can stay there, and blood never reaches to this blood or this balloon anymore, and then you can treat it because it will die out, and you will recover the patient with this kind of stent function. Also, we can embed inside the stent robot a channel of a cavity where we can put some drug, which is a TPA drug, that can open blood clot. So when you reach to the blood clot region, we apply a remote heating to open the cap that will deliver the drug in the local region, and that will open the blood clot, and so you can recover from stroke. So all these things I showed were nice mock-ups, but this is the first time indeed achieved in Hong Kong, so made in Hong Kong. This experiment was in a rat. As you see, these are X-ray images using contrast agent in a blood vessel. This is, you see the aorta, and now we are tracking our stent robot, and this is smaller than before, 0.7 millimeter. This is unpublished work. With the magnetic control, we can move it around. And the good news is with all the complex bones and organs around the robot, you see the animal is live and heart is beating and everything is moving, blood is moving. We can show that stent robot can be controlled. And here to track it, we are using machine learning. Because this is a very noisy, complex environment. To track a tiny machine inside your body, we need machine learning algorithms to track it. That's why it will be published in Nature Machine Intelligence in the near future. And showing that these robots really work in live animals rather than mock-ups. Another magnetic actuation breakthrough we had recently is we can also in real time replan and reprogram the magnetic profile. Before I showed all the soft robots with magnetic programming, but they were fixed. So now to change them on the fly, we make concentric tubes, for example. Each of them have different magnetic programming fixed. However, if we change with actuation each of the relative position of each tube, we can create different magnetic profiles and different magnetic programming by just actuating them. So this could be in a concentric tube, on a sheet. This is just published in Nature. I don't have time for the details, but let me show you what this kind of reprogrammable magnetization can enable us as new medical devices. For example, if you want to make an active catheter where you have a magnetic tip, if you apply a field, it will bend to reach a target. However, if you have an obstacle on the way, like an organ, you cannot control the tip very precisely, and you will not be able to reach because bending point is always moving. However, with our concentric tube idea, right now we have multiple tubes with magnetic programming inside. We can fix where the bending will happen, and then the other tip can move as a concentric tube and reach the target without touching to our obstacle. And you can do it more complex. You can even program now 2 bending points because of the concentric tube idea again with multiple magnetic programming. We can fix this one and that one and still reach the target because we can control exact bending points with the magnetic programming. And magnetic actuation in this case is very simple, just one-dimensional bending of the applied fields. That means now we can have multiple soft magnetic catheters that we can program individually and with the same controlled field. One can bend in one mode, other can mode in another mode, and even you can have many of them independently controlled. in another mode so that we can make very complex operations in very small soft devices. To wrap up, I tried to show you cell size, micron size, and milli-size wireless devices. Of course, we started with the concept designs and prototyping and lab testing first. Then I showed you recently live animal testing started finally. And in my group in Koç University now we can do many of these tests, which we couldn't do in Germany before. We need to show both large and small animals first. And then we need to show them their safety and function in humans. Then we will see these medical devices in the clinic in next 5-10 years. Again, to wrap it up, basically we have promising results and initial animal data, and there is still things to do with the control. I didn't show you about automated control yet. We are working on it. And as I mentioned, we need to show clinical applications and make sure that everything is safe. So with this, I'd like to thank you for your attention.
You said the magnetic profile can be programmed within the materials. Can you clarify how to do that?
Yeah, let me show a little bit more detail. So, because each element has different magnetic profile, is that right? So when they move relative to each other with another actuation modality, so their relative position is changed. That way, effective magnetization profile is changed. For example, if you move these three things together and two things together, depends on their magnetic profile, you can basically have large number of different magnetic profiles along the tube, along the cylinder. So typically they were fixed before, is that right? But now they can relatively move with respect to each other.
So the rod can move within the matrix.
Exactly. And in this case, we use a tendon-driven approach to be able to move them in a catheter application case. So they can individually move relative to each other.
I see. Yeah. But only in this direction, but not...
Yeah, okay. One dimension, but you can have a three-dimensional magnetization in each tube. So you can basically effectively get a lot of degrees of freedom. So basically, you make your relative magnetic profile with much more number of different profiles by relative motion control.
Okay, thanks.
Thank you so much for the wonderful talk. So I think I want to ask you a question regarding the physical intelligence that you talk about. So I think you show many very interesting examples that how the structure and the design, the structure complexity can introduce this kind of intelligent behavior from your devices. So I want to ask you, what do you think of in the future, what's kind of the ceiling or the upper limit from the structure design perspective? Or do you think there will be more breakthrough in the fundamentals in terms of the intelligent behavior that previous system cannot capture, or more in the application scenario? So I'm curious about that.
Yeah, thanks for the question. I typically give a physical intelligence talk fully different. This is more medical focused talk. As you mentioned, these soft, deformable, adaptable structures and materials are smart. To call them intelligent, they need to perceive environment. They need to move like these and learn or adapt. As you say, right now I haven't shown you any sensing function. We can integrate sensing function to these soft robots by making them from stimuli responsive hydrogels or elastomers or other micro-nanomaterials like liquid crystals. We have shown all these things. I didn't have time to get into those details. That means they can respond to the stimuli in the environment, for example, temperature change, humidity change, pH change, so that they can sense them, react to them in a way that they can adapt and create a relatively smart, intelligent function. So in that sense, sensory stimulus-based response is one aspect. We need to add more as a perceptual way rather than just actuation. These are mostly for actuation. The second is we need to do some computing and memory to be really adaptive and much more intelligent rather than just smarts. And the good news is mechanically these days, a lot of people, not only in my group, and now this is a bigger growing field, you can use metastructures that can have memory and that can also have computing. We have shown recently, I should have put that, we can make capsule robots that have sensory hydrogels that can detect in the body different pH and pressure changes. And they can create responses that has a logic operation, because we can make mechanical structures that can do any logic operation, Don't forget, anything we do in electronics, we can perfectly do in mechanics. I was electrical engineer by training, and I learned in mechanical engineering as a professor. Whatever I did in a circuit, I could do exact mechanical counterpart. So that means any logic operation I can do with some compliant structures mechanically. So you can do computing, logic operations mechanically, and then create a response that is after a computation and control. So in that sense, we can integrate, as you say, more sensing, computing, memory, and then we can start a little bit more next level of adaptation and learning. These are possible without an electronics, or of course, we are not obsessed. We can also integrate electronics. Then only thing is you need power. And then what we do is we can transfer power in the medical case with acoustic waves. I showed before for actuation. The same waves can induce piezo element actuation that induces electricity that we can use for onboard sensory electronics and other computation too. You can induce macroelectronic integration. So we can do both electronically with power transfer, or still pure mechanically by integrating more complex structure and material that can do computation and other operations that are needed for intelligence. It's all possible, and the field is coming there. But the current examples are relatively simple. That's why we don't call them fully intelligent yet. So they are more smart.
Okay, so faculty's finished question, students?
Yes,
sorry,
please.
sorry.
I'm wondering for the jellyfish one, I say it can insert the medicine into the tissue. Can it unplug itself, or the bio structure can dissolve in the human body by time, or do we need to take it out manually?
So in the bladder example of when jellyfish shooted this needle to anchor to the tissue, there the needle itself, it was made out of silk, which includes a drug inside. That's why it can go under tissue and deliver the drug by time. As you say, it degrades, and then the robot is released at some point. But since it's the bladder, you will pee it out, or the worst case, we pull it out. But in that case, the robot was not supposed to be dissolved. Only the needle was supposed to be dissolved. But that's a very good point that in the case of StentBot, for example, which goes the brain, or some other applications, when we put a robot in the body for a long time, sometimes we can take them out, like in the bladder, we can take them out with a catheter, or even in the blood vessels, we can take them out with a normal catheter. But sometimes they are in a very complex region that we might want to just dissolve them. Then you need to make the whole robot dissolvable. That's possible, except magnetic particles that we typically use for actuation are not dissolvable in the blood. Only dissolvable material magnetically in the blood or body is iron oxide, magnetic particles. However, they are magnetically, for actuation purposes, very weak. So that's why degradability works only for easier actuation cases, not complex actuation cases with iron oxide nanoparticles, which is possible, and we do for some specific applications. And other thing is magnetic particles, although they are not dissolvable fully, body can also clean them up, because these robots are carrying very little amount of particles that body can clean. They are cleaning a lot of junk from our body constantly, our kidneys, and our also liver. So in that sense, hopefully, also even in the non-dissolvable magnetic particle cases, they will be low enough number that the body will clean them up. But that's an important point. Some cases we don't want the full robot to dissolve by time.
Okay.
Yes, please.
Thank you for the talk. So I wonder, like, you mentioned one case where the robots that move in mucus is very difficult, right?
Yes.
And you also, I remember you also mentioned, like, for the bacteria that cause the stomach cancer, like it can kind of just reduce the viscosity of the mucus.
Yeah.
So is there a way, like, do you think it would be possible for like micro robots to locally reduce the viscosity so that it can move in the mucus easily?
Sure. That's a very good point. Indeed, already a group did it in Max Planck. Another group, not our group. As you say, if you release a chemical like the H. pylori bacterium, that it's a urease or some urease type of chemical that will change chemically the viscosity of the mucus so that you can still swim easier. It's done. Yeah, it's a good idea. The only problem of that kind of idea is, though, you need to carry the liquid, and that is typically a very small amount because you're a small, tiny robot. That works only for short duration, for some small distance. So if you want to keep moving all the time, you will consume the liquid. So that's why it is a great idea if you have only short distance navigation, which might be good enough in a specific application, then it's okay. But if you need to keep moving, unfortunately, the chemical you carry will be very limited for short duration only. But it's a great idea, yeah. All of these things are great inspiration. That's why we do a lot of nature inspiration. So we look at how bacteria do, how animals do, so that some of them are direct inspiration for creating micro-robotic versions, definitely. And people publish in high-impact journals such ideas. Yeah, very good point. Yes, please.
I want to ask this question for the stent-like design. You mean use the flow diverter to treat the aneurysm, and for that one, for the guiding of the flow diverter, is there any mechanism or special design on the structure to achieve the clamping and expanding behavior of this?
Sure, exactly. Yeah, because of time, I didn't go whole details. So you saw that it was a mesh-like structure with a diamond-shaped cavity that helped for radial compliance and bending compliance. As you mentioned, indeed, the real robot, let's say we first know the vessel diameter, the biggest and the smallest we want to navigate. And in that case, 1.5 millimeter was the maximum diameter. 1 was the smallest diameter we would want to move the stand robot. We designed it to be bigger than 1.5. Indeed, the robot was, let's say, 1.8 millimeter diameter. So we inserted with the catheter. Indeed, when we inserted, it is opening. And since its normal diameter is bigger than the vessel maximum diameter, it's always compressed. So it has already elastically deformed. In the vessel, the good thing about that is with the normal loading, it has good friction. The blood flow cannot move it. Because if I don't do any magnetic actuation, when I release the stand robot, I want to make sure that it stops where I release it. That's only possible with this making it bigger, and when you insert it, it's always spring-loaded and compressed within the tissue, as one detail. Second, when you want to navigate it, if this mesh was like that, it's not optimal. Indeed, it's hard to show, but there is a helical ring around the whole mesh that is 3D printed with a protrusion, which is very important because we are not only linearly moving the magnet, we are also spinning it. Indeed, that soft stand robot spins and propelled and pulled. And when it rotates, if it didn't have the helical trajectory, it will be inefficient and it will not even move. It will just stay in the same place. Because of the helical protrusion, it will be efficiently moved like a screw inside the vessel. So that is very important second detail that makes it movable in both directions. And then, as you said, the mesh structure again is important because the vessel is getting smaller. So it's passively adapting because of the compliance. But there's a maximum limit, is that right? So if you go 0.5 millimeter, you'll be compressed so much, it can adapt, but the friction will be too high. I cannot move it anymore easily. So that's a whole paper with 2 papers with details of modeling and experiment characterization. Friction is very important, morphology, helical trajectory, and the compliance radially and bending-wise are very important because we are not only moving in the vessel, in the bifurcation, we need to be able to turn and bend. So that's why there's a lot of optimization of compliance and the friction contact with the tissue and compression to the tissue so that we are stable anytime, because for safety, when I take my magnetic field off, I want to make sure that I stay where it is so that I don't go randomly undesired place and I don't want to kill the person. So that's why the stand robot was designed to be very stable in any point and controllable precisely because of the compliance and the helical contact with the tissue surface. Yeah, thanks for the detailed question. Yeah. Yes, please. Yeah. Great, great. Yeah, please don't hide. I mean,
yeah, it made me a little bit nervous. Thank you for your presentation, and I'm really interested in your paper about the cilia areas, and they have programmable motions. So I wonder, does they have any potential use in biomedical field, or because nowadays there are many cilia-based array platforms or bands that can for the sound encoding and the drug release, and also some people have designed robots with a cilia-based band that have a viscosity field for some motions. So I wonder if it's possible to use in this.
Yeah, definitely. As you say, there is a lot of literature in theoretical and experimental at different length scales about cilia arrays. As we said, the basic point about cilia arrays is fluid manipulation and object transport. So the basic physics is when the cilia moves in a coordinated manner or in any controlled manner, it controls the flow around the cilia. That can be used first for propulsion. As you say, if you take the same cilia, which we showed in the new Nature paper that will appear, on a device, indeed, if you actuate the cilia, that's how organisms swim. The propulsion of the robots can be enabled. Because a lot of organisms use cilia for actively swimming. Tens of hundreds of organisms use tiny hairs on their body. Our hairs are passive, but the active hairs make them swim. So in that sense, it's a great technique for propelling robots or devices in the fluid media with high viscosities. If you are bigger cilia, you can move in high viscosities. If you want to move in low viscosity, then you need to make tiny cilia like our new work. And as you mentioned, in many devices, you want to do fluidic control. This is one new technique, which is very compact. But as I mentioned, for us, rather than the lab-on-a-chip type of devices, there are a lot of options. The novel application here would be, as I mentioned, in the body, we have many cilia in respiratory system and the brain ventricles. And there are patients with problem with cilia genetically, and then their respiratory system doesn't work, or you make a surgical change in there are some operations, they put a synthetic catheter, and if you don't have the cilia, by time they get mucus, and that's why our system always keep cleaning. The cilia cleans our respiratory system. So one application that a Harvard medical person asked me is, can we clean this device by time? And yes, it's possible. And also brain ventricles, as I mentioned, some patients have also problem in the cilia in their brain ventricle. If the fluid doesn't move, your brain explodes. So that's why they need to do operation surgically to create, they take the fluid out or they pump the fluid. So in those cases, cilia, wireless cilia arrays that I showed could be very interesting for pumping the brain fluid or helping for your respiratory system. And as you say, there are many other creative ideas of fluidic manipulation that will make you some new device applications. So there is no end of creativity. I just showed more robotic fluid manipulation control and object transport. But yeah, as you say, fluidic control has a lot of ideas. You can mix fluids. You can do a lot of things like a microfluidic application device that has much more dexterity and controllability than any typical microfluidic device. That's the advantage.
Okay, so probably I just represent all the PG students to ask you one more question, the last question. So we have lots of graduate students here. So as a senior, can you give them some advice since you publish a huge amount of work on literature science and whatever, right? So what's the most important thing they should remember in order to achieve a very successful study as a graduate student?
Thank you. Graduate student, wow. Okay, thanks for the great question. So, I mean, first rule about graduate students and PhD is you need to have fun, right? So if you are not excited about doing research, don't do PhD. You need to be first excited and highly motivated, But then whatever you're doing, you need to really like it and have excitement and fun. And that fun doesn't happen only with your personal interest, but also happens with the team. You need to work really closely with your lab mates or other groups or even around the world with different people. So in that sense, yeah, I mean, you need to make sure that whatever you do and how you do should turn into fun. Otherwise, if you suffer from it, it will be psychologically and also scientifically not productive. So we are doing these things really. Research is curiosity. Crazy is right. We create these crazy problems and we solve them. And we hopefully expect them to be useful also. But all these things are done because we really love it. There's a lot of creativity and freedom of things to do. But unfortunately, a lot of dynamics of publishing and politics of science, I call it sometimes, and many other factors, and how you are mentored and the group dynamics sometimes make people suffer, so don't allow that. And again, the fun part happens with everything, doesn't happen because you're only excited and positive person. So we need to also, I see that more and more, psychologically, our graduate students are more fragile than my time. We were so robust and work hard day and night without any psychological issue. Now, even us, everyone has a lot of pressure and the world is changing in different ways. Let's make sure that psychologically you're always strong and get mentorship. Don't, I mean, these days the good thing is, in my time, oh, you know, if you have psychological challenge, it's very shameful to talk about it or go to a mentor, or we have a psychological counsel in our university to help students. These are nothing now anymore shame to talk and also get help. So all these things can happen in life. But again, at the end, if you have fun and succeed, and don't forget, I tell my students, I don't care about any publication. PhD is your work. At the end, you will be proud of or you'll be shamed about it. So that's why try your best to have fun and get useful things. And don't, in Asia, the big challenge is don't get obsessed with these publication impact factors, numbers. The quality is more important. I think science is now, unfortunately, less fun sometimes because everyone is saying, oh, you know, how many papers I have, which journals, impact factors, and counting those things and citations. No, I mean, what we need to have at the end is all these researches we are doing is for impact. With even few papers, I have students like when you spend 4 years with no other paper and get this Nature paper out, if someone look, man, what did this guy do, produce in 4 years? But eventually, like rather than the number of getting low quality and number of papers, persisting and really focusing on the impact, and at the end, rather than these metrics, you see that a work comes out that really impact your field by the quality of the work, but also the novelty of the work. That's, I think, the most exciting thing we should have. So, yeah, I mean, all these factors and things are the important parts of having a productive, but and also again fun PhD. And don't forget also, this is a social place. Fun doesn't happen only with science. Socially, also, it's very important. The best collaborations happen during having a beer, not having boring, serious meetings. So that's why all these friendships are important. As I say, I try to be friends with all of my students. I never thought I'm this and they are there. I'm one of you. I'm a human. I also have problems in my family sometime, or my personal life, or you know, some days are great, sometimes are not necessarily the best. So I think important thing is you should think also this graduate study as a friendship and social system that you need to all support, help each other, and be friends. You cannot be friends with everyone. That's also okay. But yeah, I mean, all these things are lifelong experience. And I think, yeah, PhD is really a very important time of your life. And hopefully you have a positive one that you continue your future. And more also they're expecting PhD these days than old days. So even if you go industry and startups, yeah, it's all great. And hopefully you will have a great future after a fun PhD. So that's a brief, or not brief.
Okay, I assure you what Metin said is true. I usually met him in the forest, not in the lab. Okay, now let's thank Metin again for this great talk.
Thank you very much.
And thanks for coming.